Okay. Our next speaker is going to continue on with some of these great practical insights about various like data considerations and methodology considerations. We now have Kate Highnam, and she's going to be presenting adaptive experimental design for intrusion data collection. So I'll pass it off to Kate.
Thank you very much. Hey. Waiting for some slides to load. I'm Kate Highnam. I'm a PhD student at Imperial College London in my final year. Hint, hint, nudge, nudge. This is my second time presenting at CAMLIS. I'm very excited to be here again once more. I have this new paper out, Adaptive Experimental Design. As we finished lunch and we're kind of settling into the afternoon, let's stretch a little bit. How many of you have heard of experimental design before? I took a science class. Yes. Should be more hands. So my co-authors are kind of interesting, so I just want to mention them here really quick. So a few of us are in security, so the first two and the last two, some in national security, but the middle two are very interesting backgrounds. They are my friends over at Imperial who work mostly in healthcare and RL in healthcare. And I had a very interesting conversation with them last year when we were discussing methods that people had used during COVID treatment testing. So if we have a new treatment and we're trying to cure people, what methods do we use to try and understand whether the treatment has an effect? Now, I'm using this phrase very specifically for those of you who maybe do causal inference or understand causality. Yes, great hands. Should be more hands. Yes, yes. Okay, kind of creeping up towards the end. So that's kind of what we're talking about today. So I'll mention the ties to healthcare later on. I'm very excited about bridging gaps. I love pulling ideas from other fields that maybe don't make as much sense in cybersecurity, but showing that they can be. So we're going to show how we can do a control study in cybersecurity using adaptive design, which is a method that I took from healthcare. And then we're also going to apply it in one of the first interventional studies using honeypots, which is going to be my running example. So you can find more details in the paper, which I tried to upload to archive right before this, but it's being very specific about the bib file, so I'll do it later. But yeah, so in intrusion collection, data collection, right? We're trying to understand adversaries. All these different black hats are attacking in all these different ways. And you can simulate attacks. You can purchase log data from third-party vendors. You can grab your own logs. And this is typically how we get data and then study it to then develop our defenses. And this is good. We call this an observational study, right? So we have no control when we grab logs from 3 months ago to how we grab logs today, right? There's no clear ties between the two. So they're very easy to acquire, this kind of data. You can either purchase or record it. But there's this potential for bias where we assume things that maybe we shouldn't be. So that could be something like the state of my environment is exactly the same as it was 3 months ago. How many of you are concerned about that? Yeah, a few hands. And some of the studies that we might run to try and collect this information, we have a piggy bank that tells us how much money we have. And then we say, okay, so I could probably run honeypots for some amount of time. Here's some numbers. Let's throw them into the wild, wait 6 months, and then take a look at that data. But the environment's changed. So how relevant is that data today? So today, I'm challenging that. What else can we do when we're collecting data? Do we just have to observe the environment, or can we instead intervene and understand our environments in a very specific manner? So maybe the data isn't as generalizable, but we can understand as the world is changing what this change that we have done based on a control group and our intervention. And I'll go into more detail as this is kind of jumping around. But it is relatively difficult to acquire. So I have to have a good understanding of my environment. I have to have this hypothesis, and I then go into the environment and I make that change, and then I have to collect that data. But we can control the characteristics that we're studying to help remediate bias. So we mentioned in the last talk, right? Bias is a huge concern in our data sets, especially when we give it to a model and understanding what the model is trying to do. So we want to limit how much we could bias our model. And I'm particularly curious about how models can be tricked by spurious correlations. So if I can control the bias in my data, confounding bias, what improvements do I see in model performance as I generalize to different cases? And the other benefit with interventional studies is we're getting the counterfactual. What would have happened if I didn't change the environment? Or what would have happened if I did? So that's the kind of data collection that we're considering today. Now, in interventional study, essentially, you need to fill in these blanks. So just to ground us in cybersecurity, I'm going to continue with my running example of honeypots. So we have our population, let's say some Ubuntu servers that we deployed to a single cloud. And we're applying some treatment. And I'll touch on this a little bit later as the specific treatment that I used, but this is a method talk, right? I'm just talking very vaguely about a change that I am making. So we have some control that is one version, and we have a treated version that is slightly different. And the key word there is slightly, right? And that's our treatment, or when we're experimental study, it's the same thing, right? So our intervention. We then have our control group, right? The part I didn't change, and then our duration. And this is typically dictated by some piggy bank. How much money do I actually have? How much can I afford? This will come up a little bit later. We then have some objectives. So did the treatment do anything, right? That's the whole point of an interventional study. I've changed it in some way. Did what I thought would happen actually happen? And then we're telling whether that happened based on events of interest. So for a honeypot, that might be whether an exploit of a particular kind occurred on a host. And then, of course, we have to have some endpoints. So do we run out of money? That's always a pretty big concern. Now, you might have already seen, and I alluded to this before, right, or stated earlier, that it's related to patience. So I sat with my friends and I said, what if we take your patient studies and we actually conduct it in cybersecurity? So I started mapping words. I think that's the clearest way to do it. So when we have a trial, a clinical trial, we're actually studying, comparing honeypots with and without a vulnerability. We defined our study population before, and here our population has patients, and our inpatients are honeypots, or just servers, or hosts, or machines, whatever you want to be. We then can recruit more. And this is actually really interesting when you talk to healthcare people, because in their studies, they say, I am only recruiting females between the age of 20 and 50 who have a certain income, et cetera, et cetera. And they have to assume a lot of similarity. But in cybersecurity, we actually have exact duplicates of machines where the only difference, especially with honeypots, is the IP address or whatever changes that we specify. So some of those assumptions, it's actually stronger or easier to make for us than it is for them. So we're trying to now reverse apply this for some of their simulation techniques. Now, of course, we have our disease, which is a very easy mapping. We already talked about viruses. So for this case, it's just the attacker technique used to exploit. And then we have our intervention. And to make it more security, I've translated that to the word corruption instead of treatment. So instead of trying to assist people and defend, I'm looking at intrusion data collection. I want intrusions. I want to corrupt a device so that I can collect more information as to how people are exploiting this particular vulnerability. Now, the gold standard in healthcare is to use a randomized control trial. And it typically looks like this. So you have some idea of how long your study can occur. And instead, you chop it into stages. And you do that so you can have this interim analysis to make sure that nothing went awry that you didn't expect. And if it did, you stop yourself early and you try and save as much money as possible and reevaluate what you did wrong and hopefully don't do it again. So you start by recruiting some population, some number, which I say pull out of hat now, but we'll go through the statistics in a second. You then randomly assign, hence the randomized control trial, randomly assign them to either the control group or the treated group. You then observe and log some information for some amounts of time. And then you go through your interim analysis, which tells you whether or not you progress to the next stage or you've reached some kind of endpoint and you stop the trial. Hopefully this makes sense. So in honeypots, we would go to our piggy bank and we say, how many stages can we afford? Okay, I'm then going to determine how many I think I should afford and deploy that many. And you can see the different blue and gray, maybe if you're sitting a bit closer, as to who we assigned to the control and who we assigned to the treatment, and they're different in every single one. So this one is an example of 3 different stages. Now, I could say I just applied this, and that would be a very interesting paper. But the other side is, can we do this any better? Can we come to some conclusion or get some different objectives going for intrusion data collection specifically, and alter this method? And that's what we did. So we have adaptive design. So we actually adapt based on the incidents that we see at every stage. And our goal is to do the exact same thing RCT does. So we want to confirm the interventional effect as quickly as possible. But we also want to be able to adapt so we can save some money while encouraging data collection of events of interest. And that's where our method really comes through. And we do that with 2 major changes. So to compare and contrast, so hopefully you can follow along, it's a little clearer in the paper. We take the original observational study, which would look something like this. So we have our budget, we have some trial duration, we deploy some number of only corrupted versions of the honeypot, or interesting observations that we're trying to look at anywhere else in cybersecurity, right? We've heard a lot of different fields throughout the day, whether you're doing insider threat or SQL servers or whatever. And then you wait some amount of time, you collect the logs, and then you clean up. And that's how you observe. But you have no information as to what would have happened had we not been with a certain vulnerability, had we not had a certain port open, had we not had something else, that counterfactual information. And so in control trials, it looks a bit more complicated, but I promise it's not too hairy. It's just the same graph again, I just turned it sideways. So instead of saying we're just going to deploy some number based on our budget, we're actually using power analysis to determine how many we should deploy based on how much error we're willing to accept. So here we're looking at type 2 or type 1 error, so false positives and false negatives, and we're saying we want to limit this as much as possible. And we want to see how many of each type we need to deploy. So randomized control trial, you do 50-50, half control, half treated or corrupted in this case. And power analysis will spit out some number, and you can pick any function. I asked my friends and they were like, as long as you're consistent. So you just go on a website, you find an equation that makes sense to you, and then you put in these values and you get some number out. It's consistent. But at least it's documented and detailed so we can all agree on something. And then you deploy it, you wait some amount of time, you then check for whether you stop early, right? So you have those preset conditions based on your logs, or for some reason it turned to capital B, budget, and the total number of honeypots that you could actually afford to deploy. And then you rinse and repeat until you stop. What we changed is we added this survival analysis. So we said, that's great. We have these logs. Can we quickly scan through them, see if the events of interest occurred, and if they did, update our initial assumptions on the proportions of whether the control group got exploited and the corrupted group got exploited. And all we did was then update those values and put it back into power analysis in between the stages. So every stage, we're reassessing how many we need to deploy and then deploying that number to see if we can encourage infections. So that was the first change, right? So we wanted to see if we could save some money by limiting how many we needed to deploy. And now we're trying to encourage observations. So the only other change is changing the objectives. So in a clinical trial, they're mostly trying to do a confirmation of a treatment effect, but we're doing both. We're trying to confirm there's evidence of an effect while also trying to maximize the recording of events of interest. We want to see as many intrusions as possible. And we want to make sure that whether we pick the control group to study or the corrupted group to study, we want to maximize that information. So our study at the end of the day will always give us really interesting data to look at later. Now, I did a pilot study, or at least I like to call it that. This is my presentation from 2 years ago, for those of you that were here as well. So this is a data set that we publicized. I promise the QR code isn't sketchy, as I was informed last night over dinner, which is funny. But it's a data set that I was hoping for unsupervised anomaly detection research. And it's the same honeypots that I ran before. I was just reusing them to see if I could study this particular vulnerability in a different way. So these are the details of my study. in a summarized version. The much more thorough version is in the paper. So we have our population, cloud-based Ubuntu servers, again, all from the same cloud provider. We then studied 4 regions within the US, right? So East and West Coast split into 2. And we just were curious as to whether there were any trends on the events of interest between the regions, whether that could bias our study. We'll go through the results in a second. Now, our corruption that we chose was just a simple SSH vulnerability. So on 4 dummy IT user accounts, we accept any password. And then our control group was just the same exact accounts, but instead we only accept the word password. So we have some assumed rate of incidents on the control group of how many times we thought it would be exploited in within the trial, which we chopped into 3 stages. So it's 4 hours per stage. And we said maybe like 1% would get corrupt or would get exploited. Then in the corrupted ones, we were like, maybe like 0.4. So based on our pilot study, we had this statistic as to how many we thought would be exploited in the 4 hours. We then have our objectives, which I mentioned before, exactly the same. And the events of interest is just, did anyone successfully log in on any of these 4 user accounts? And then we have our endpoints, because I could only afford to have 200 honeypots per trial. This is a relatively small trial, but yeah. Pockets are small. Academia. And then to limit error, what was interesting also what we could do is, because it was so affordable relative to clinical trials, a lot of times the limitation is that while we can use power analysis and get this really strong number that we are sure that will give us some confidence that we are not committing a type 1 or type 2 error, the number that it usually requests is too high for recruiting humans into a study. But for us, it's very affordable, so we could push the limit. So typically alpha is set to like 0.1 and beta is set to 0.2. We pushed them down as much as we could afford to, and then tried to carry on with that. So here's some results. Sorry, they're not so pretty. Vanilla just is the observed study that we ran at the same time. So we deployed 140 honeypots for 12 hours for the observational study. We saw 137 attacks, which of course was the most. But comparing the stage trials, we deployed fewer control because we found, or the method found autonomously, that the control group didn't get infected as much, which was the goal, right? We wanted to see adapt in live time with real attackers. And it deployed fewer honeypots overall while seeing more attacks. Woo, goal achieved. Now, what was interesting also, though, over the stages. So in the very first stage between RCT and adaptive design, you deploy the same number, right? The same power analysis calculation goes into both. But we actually saw a higher number of control instances being exploited than we anticipated. And so the method updated, as it should, the rate of incidents that it saw in the control groups. And it was only in the eastern regions for some reason. And it said, okay, we still need to deploy some controls in the second stage just so it can confirm that the treatment effect is truly present. And because the corrupted ones had higher rates, we deploy more in the corrupted group. Then in the second or the third stage, after we observed the results of the second, we actually deployed no control because none of them got exploited. So it just goes to show that it works. That was all I wanted to do with the study. The data is kind of interesting, but the most it told us was some interesting staggering kind of occurred in one of the trials. So this is the randomized control trial. So you can kind of see a little bit of an echo between the regions, which was interesting. There were no obvious patterns to me when I looked at the IP addresses to see if there's like a linear scanning or anything like that. And then the other thing that was interesting was in the stages. So again, it was over 4 hours. And some of these are survival curves. Sorry, I probably should have mentioned. So it just says, as they get exploited, we reduce the likelihood that the honeypot would survive by the end of the trial. And that's what the final result is. But they weren't as consistent as we thought, which kind of shows that our 4-hour windows are probably not as stable as we thought they would be. So if we could afford more longer stages would probably give us better information. Yeah. In conclusion, We came up with this method to challenge the way in which we collect intrusion data to see whether an interventional study could be useful, could be interesting, and could be done better. We then showcase our method using honeypots. We confirm the correction. So the corruption effect, we could have said after the first stage that the control group obviously doesn't get exploited as much as the one that we corrupted. So we could have ended after the first stage, but because of the second objective saying we wanted to increase the number of intrusions that we collected, we kept going. And by the end of the trial, we collected fewer honeypots and we saw more attacks, which is great. So future work. We are currently working on implementing an interesting toy website to see if people will scan, hit, and exploit multiple vulnerabilities. And I don't mean just 5 entry points. I mean like 3 entry points and 2 that they have to reach in the sequence. And then even more so. So if I close a gate on my web app and I know that people are scanning and hitting this, does that affect what they do in later stages of the attack? And this is targeted information that this kind of study allows us to do. I'm also looking at doing some causal analysis on existing data sets and seeing if this method will help us remove bias. So if I think from a data science perspective, I've looked at the features and I seem to be skewed in a particular manner. Can I intervene or do something in my environment that collects data that would help unbias or unconfound this data? So that way, when my machine learning model comes in and tries to learn all the different correlations, it doesn't have that spurious correlation opportunity, at least as obviously. So thank you very much.
Thank you so much. That was really fascinating. Okay, we've got a few questions coming in online. Please raise your hand if you have some in person and we'll hop back and forth while we have time. So did she just announce a CTF? Haha, okay. All right, so a few different comments here. Let's see, we'll start with this question here. Is there a connection between this adaptive design analysis and Wald's sequential probability ratio test, or SPRT? So Art says SPRT was proven to be strictly more data efficient than offline batch hypothesis testing. So he's wondering if this might be related to that or if that's something you're familiar with.
I'm not familiar with it, so I'll definitely take a look at the chat afterwards. Thank you.
Questions here? Let's see. Okay, so there's a comment. I think this is in reference to the offhand comment you made about the East having more of the exploits on the control group. It's just that East 1.2, someone believes it's used more often than West. That's a possible explanation. And he also mentions that you could consider using non-US hosted honeypot because cyber criminals prefer US targets. So that would be an interesting variation to look at. Okay, question in the back.
What I think I missed it, and I'm sorry about that. But what was the intervention you actually? What was the intervention you were doing and then measuring?
Yeah, so the intervention was the SSH vulnerability. So accepting any password to a certain set of user accounts. And the control was only accepting the word password, so slightly less vulnerable, and just to see if people were scanning for it. Because we might assume, based on whatever user accounts that I've put out, I could have come into the study and said, I don't think anyone is scanning for these user accounts with this password. And having a control confirms if that doesn't happen, right? They wouldn't have deployed in the second stage, but they did get exploited. So it's always good to have that control is what I was trying to show. That's kind of a toy example, right? Like I think we all know that accepting any password make us more vulnerable to exploit, but it was just to showcase the method and how it works.
Okay, thank you.
Thanks, Josh.
Yeah, I was kind of curious on a similar note, I guess, like in terms of the motivation of this, it seems like, yeah, there's these two different objectives, right? To prove the effect of the treatment and then also to collect more data. Is there one or the other that was kind of your underlying motivation that you that drove the coming up with this methodology, or yeah?
That's a great question. So it was actually kind of an argument that I got into with my friends because the clinical trialists are all saying, you know, it's only to confirm the intervention. I was like, yeah, but we want to see more attacks. We want to see more diseases hit the people. Like, not in the people sense, but in the study, of course. Sorry, gotta be careful with the terminology sometimes. Yeah, so it was an interesting dichotomy sitting on both sides. But it was interesting also that we could encourage this and have that information throughout the study of whether or not this exploit could increase the rate that we observe the events of interest and then log more interesting data.
Yeah, that makes a lot of sense. I think you wouldn't be encouraging more disease, you'd be encouraging more cures anyways, right? So you can make that argument. Okay, and then one last quick question. Someone's curious to know how you selected the usernames for the SSH.
So that was just based on our pilot study. Ask Zach.
Excellent. All right, that's all the time we have. So we're going to move on to our final talk. Let's thank Kate.